kernel methods, in particular range regression. Today we will discuss the four-vector machine, which are another instance of kernel method, very famous technique. But so let me summarize. I think I wrote it down here. What are the main message of last week? So what is really important? Of course, we need to work with the details a little bit, but. So the first thing we saw was the idea of regularization, and in particular range regression, as a means to ensure that you have a unique solution of the problem, and the solution is stable. So this is as opposed to just do empirically risk minimization. So we motivated that, and we arrived to this problem. So we do our linear regression by minimizing the sum of the error on the data, which is the first term, plus lambda. And lambda is a very important parameter. It's a positive parameter, which is called a regression parameter. Right? Plus lambda times the square norm of the vector W, right? The vector which determines your linear regression. And here, for simplicity, I assume that the regression function is homogeneously linear, but we can easily add one more parameter here, right? But it can always be included in the vector W and also the vector X, so just avoid the issue of the parameter V, but it's just a mathematical detail. But the point here is that you find your solution by minimizing this function, which is the sum of two terms, and the idea is that these ensure the solution is unique and depends continuously on the data. But also, it is more important, the solution has certain properties. Which I want to describe briefly now. And this we understand if we go through the single value composition, which we quickly reviewed last week. So the final result was this, right? So here you minimize over W, and since the objective function is quadratic, you find out that when you set the data equal to 0, you need to solve the linear system of equation, like in the squares, and this is the solution. Now, if you use a single value decomposition for the matrix X transpose, you can rewrite the solution in this form, where you see that the vector W is a linear combination of these vectors Ui, right, which are the left singular vectors of the data matrix. Okay, the data matrix is here is X transpose, right? So this, or perhaps. Yeah, X or X transpose, right? So this vector Ui are d-dimensional, right? Because the vector W is in d-dimensional space. And so what is interesting here is that the coefficients associated to the which form this linear combination depend on the regulation parameter lambda, right? And depends also on this parameter is lambda I, not to be confused with lambda. So perhaps in the notes we could have called the parameter lambda gamma or rho. We have different things. Okay. So now here you see that if the regulation parameter lambda is large, the coefficient is small. So eventually, if lambda goes to infinity, the solution is 0. So your guess is just the 0 vector, which doesn't make much sense. So you don't want to put lambda. You don't want to let lambda go to infinity, but somehow you want to let it be big enough so that you don't overfit the data. So there is this idea that if lambda is too small, you will overfit the data. right? Because you have less data points than number of parameters. So M, the sample size, is smaller than the dimension of the input space. The other point is that in these coefficients, right, also contains the parameter lambda I, right, which are, so lambda I are the eigenvalues of the gram matrix, so of this matrix, or perhaps this, they are the same, right? So now what happens here is that if lambda I is large, right, this will play a bigger role, right? So and we know that the big lambda I corresponds to the principal component. So here what you are doing, somehow you try to favor principal components for regularization. So this is the first message of what regularization is doing. Right? This is important when we go to kernels, right? And before going there, what we did was to describe, so the other important idea is this idea of primary representation and dual representation, right? Which is the kind of the trick or the gate through which we introduce kernels, pretty much. And so the other point that I highlighted last week is that you can also write your solution as a linear combination of data points. Okay. Right. So if the number of data points is more than the dimension, which is typically the case, this is a more compact representation because you only need to find these parameters on the I. Right. And there is an equivalent system of equations for alpha, which you solve here to find the parameters. And it is less expensive because you have to invert the smaller matrix. That's it. But there is something more that we see here, which is key in understanding kernels, right? Now, before speaking about kernels, we spoke about basis functions and feature maps. So we said, what about doing linear regression in a nonlinear? What about doing linear regression, linear expansion in a set of basis functions, which are nonlinear functions of the input? Right? So what about repeat what we've seen so far with these different basis expansion? Right. So this is called the phi is called the feature map. Phi of x is a feature vector, right? And so a typical case that you can think of that the component of the feature vector are kind of monomials of the inputs. So it will be the product between one component of the input and another component. So they are nonlinear functions. Or they could be sines and cosines, other things. So now we are interested in find the parameters of this expansion. So we expand. We said we look for a regression function, which is a linear combination of these features, much like before. And so here, what is important is to understand that we can find the solution of the regularization problem with this involving these parameters, like this function, without knowing explicitly the feature map. And the reason is that if we work out the dual representation, we only need to know inner products between the feature vector for one input, say generic input x1, and the feature vector for another input x2. So we need to know the inner product between these two feature vectors. So you see these already here, right? when we do the linear case, right? So here, so what will change here will just be to have here phi of xi, right? And here will be the inner product between phi of xi transpose phi of x, right? So x is replaced by phi of x. And here, in this equation, the elements of this matrix will be the inner product between phi of xi and phi of xj, right? Because this matrix is m times m, x transpose, and has as element ij, xi transpose xj. So again, we will replace that. So pedantically, we write this. Is this clear to everybody? So this was an important. So once you understand, I think it's kind of clear, perhaps, but before you understand, it will be very confusing. So please ask. Yes.
Can you explain again why do you use this?
I'll tell you what. Yeah.
The last part, can you explain it again?
You mean this part? Yes. So if we do a linear regression, right? We're looking for just a vector w, and our function is w transpose x. We can work out these equations, right? So the solution here, which minimize our regularized error, is linear combination of the data, right? Where the coefficients alpha I, they form the vector alpha, which is n-dimensional, are obtained by solving this equation. Now, this equation involves a a gram matrix, which is a m times n matrix, which is x transpose, right? Because x is an m times d matrix, which has, say, x1 transpose as the first row, dot dot dot, x m transpose as the last row. X transpose is the transpose of this matrix. Then when you do x times x transpose, matrix product, we form a matrix which is m times m, and the elements of this matrix are these guys. So they are the inner product between data point I and data point j. Good to go through this exercise. We just matrix multiplication. So you need to solve in a system of equation to find this coefficient where the only knowledge that you is brought from the data is through inner products. So the data points appear only as paired inner products. So if you replace data points by a feature map, and magically, as we have seen some example now to discuss that, you can compute the inner product in these feature maps. The result is this the kernel function. Then you can work directly with the kernel function. Okay, so this is maybe the most important point of the last week lecture, that we can work directly with kernels without knowing explicitly the feature map. So kernel carries inside implicitly some features which you don't need to know to do all this computation, to train the method, and to classify the points, to find the predict new inputs. Right? So prediction is done by this function, so f of x, and again f of x is a linear combination of kernels. A linear combination of these guys, which okay, so this is the kernel. Is it okay? Does it make sense? Are you confused? So regularization, interpretation of regularization. Does it work? Regularization, interpretation. I'm sure it works. I don't have a good feeling. Not sure. Yeah, okay. So we saw regularization, interpretation representation, regularization, is primary dual representation, right? And then, using this dual representation, we can work implicitly with feature maps for kernels. And the last thing that we saw last week, last important part of the lecture, was what is a kernel, how to check that it implicitly hides a feature map. So this is very important, because if we decide to work with kernels, we need to check that. And what are examples of useful kernels, which you can use in your favorite application. So, in order to answer that question, before saying that, and so once again, so this idea of going for kernel is kind of pleasing because the feature vector can be very high dimensional. In fact, we even kind of said, but we didn't discuss in detail, that it could be the feature vector could be infinite dimensional. Right? It could be in a Hilbert space, which is basically a space of sequences which you can sum up, right? When you square them. But that's not so important for the course. If you are very interested, I can open a parenthesis on that, but I would say it's not important to have a good understanding of this stuff. So it's quite pleasing, this idea of kernels, because we can work with many features at computational cost, which depends only on the sample size. Right? So it's really cool. Right? But so we need to check if the kernel is valid, right? And so the kernel needs to be polysemi-definite. Right. So there is this result, which in part we proved, right? Which says that if you start directly with a kernel function, then this is a valid kernel, so it hides the feature map if and only if it is polysemi-definite. And this means that for every choice of the data, the ground matrix is polysemi-definite. Okay. So this is the ground matrix, right? So it's called K of Ix, It's a symmetric matrix for sure, if K is symmetric, but it also needs to be polysemi-definite. Okay. And we can prove the full result, but what is more difficult to see is that if you form the kernel from a feature map, it is polysemi-definite. The way around is more complicated than this improvement. If we accept this, then we present several examples of kernels, and so in particular, polynomial and Gaussian, right? And there are different ways to, yes, please.
So is this true in other spaces or just in Hilbert space? Because you were giving us examples of feature maps that weren't in Hilbert space. You say it's different only if it's Hilbert space on that slide.
Yes.
Is it true for other spaces?
They need to be a Hilbert space. Okay. Yes. So if you start from a kernel, the feature map might not be finite dimensional. It could be infinite dimensional, so it needs to be a Hilbert space. So this is where this idea of Hilbert space plays a very important role. But I think we don't have the time to go for the Hilbert spaces. But so if you start from, maybe I don't like this microphone. If you start from a Gaussian kernel, the underlying feature vector takes values in a Hilbert space. So there are some technical details which, since perhaps the nodes are already quite mathematically involved, they can always be more mathematically involved, but step by step. So you can find some information about these Hilbert spaces in the book of Christianini and Taylor, for example. So we saw several examples of kernels, and so there are different ways to show that the kernel is valid, it's possibly definite. And so one way is directly prove what is written here. The other way is to argue that it can be constructed from simpler kernels. And we saw that kernels are closed under some operation. So if you have two kernels, now by kernel I mean quasi-definite. The sum is a kernel, and the product element, the product of these two kernels is a kernel. The multiplication by a positive scalar is a kernel. So through these properties, you can do some of these operations, and then you realize that, for example, the Gaussian kernel is a kernel, or the polynomial kernel is a kernel, etc. So this is something important to digest and understand. And I think that's it from last week. Maybe, and we prove some of these results. So we prove, for example, that the product kernel is a kernel. There is a proof that I presented. So in a way, so an interesting kernel was this infinite polynomial. Right, so that's, and I stress this quite a bit, right? So, so you can form kernels which have an infinite number of features. So one is the Gaussian, but one in which you see, you touch with the hands what these features are, is this infinite polynomial. And so this line describes what the features are. So they are, for example, in one dimension, the features are just the power of x. Right? But here, what is important, as I tried to stress last week, is that these, since this sum, right? So when R goes to infinity becomes a series, it needs to converge. So what happens is here is that the features, right, which are the component of phi of x, becomes smaller and smaller as the degree increases. Right? So what happens here is that although your model, so the function that you learn, is a linear combination of it's a polynomial of arbitrary degree, you kind of put, you tend to favor low degree components. Right? And this is important. This is why the stuff, if you apply to data, to a bunch of data points, there will not be infinite, it will be finite data points. That's why this stuff will work. Because you try to favor simple functions versus complex functions. Complex functions are functions which have dominant high degree components, so they oscillate a lot. Right? So it will be more complex in that sense. This is very much hand-waving, but it is true. You can read books which are just devoted about spaces of function, why they are smooth, so why they concentrate on low frequency basis functions. Another example is the Fourier function, which are Fourier expansion. You concentrate on the low frequency basis. This was very densely explained in the last slide of the notes. So certainly, if you want to have a complete picture of the stuff, you need to read more books which are devoted to this topic. The exam will not ask you to derive new things, but I would say that what I mentioned today, perhaps with some less emphasis on these infinite features, is important to somewhat address. Yeah. So it was a long review. Any last chance for questions before I go to the next topic? Okay. So we discuss now some similar ideas. Again, there are similar ideas, but so they're called support vector machines. So first of all, now we discuss about classification problems, binary classification. Last week we discussed regression. And at least initially, the idea here is motivated by some motivation comes from geometry. So the idea is the idea of finding a line or hyperplane which separates the points from one class to the point from the other class, and it tries to do it in an optimal way, kind of maximizing the margin, whatever we call the margin. So we'll review and we'll describe the idea of optimal separated hyperplane. Then we'll discuss how to relax these to problems which don't allow for a linear separation, but only to approximate. So we'll make some mistakes in training data, but you can still speak of optimal separating, soft optimal separating hyperplane. And then we discuss how to make these nonlinear for kernels, and this is what are called support vector machines. And then discuss why this is like, it's very similar to regularization. So, right. So we have our parent set, and so now yi is either -1 or 1 to the plus difference. And we want to find a linear classifier, right? So what we do, we want to find the weighted vector W, right? And the threshold B. So here I also speak of B, the threshold, such that when you take the sign of this function, you get back the label, the class label. Right? Okay. So we need to wait a little bit, but so that the picture I can make it here. So we have some points here. Okay. These are the plus. We have some minus. Here, like this. The minus. And you want to find a line which separates them. Right? We just call it. What we call a perceptor. Right? Take the sign of the function. But, so what we want to discuss now is, since there are many lines to separate the data, so we will assume the data are separable, there are many lines, how to choose one. Okay, so this is where I'm going. So before we do that, we need to introduce some notation, which is a bit painful. Also, there are also symbols, but once the notation is clear in your mind, you will see that this stuff is simpler than what it looks like at first sight. So, we need to remember what the hyperplane is. So, a hyperplane is a set of points to satisfy this linear equation. So, there are all the points that are on this line. We speak of a hyperplane because we are in a high-dimensional space. Okay? So, a hyperplane is a set of points in RD such that y transpose x plus b is equal to 0. Also called an affine linear space. Okay? One-dimensional affine linear space. Because it doesn't go through the origin. If b was equal to 0, it would be a linear space. As I said, we assume that the data are linearly separable. So which means that there exists a hyperplane, so there exists the vector W and the constant b, such that these equations these inequalities are satisfied. So it means that my linear function has the same sign as the label of the point. That's what this equation means. Right? So yi can be is plus. If yi is plus, so plus 1. What is it? The value of the function must be positive. If yi is negative, must be negative, so that the product is always positive. So when W and B satisfy these inequalities, I call this hyperplane a separated hyperplane for my data. Okay. And here, so there's a detail. I assume that the data are strictly separable, so they don't. So these inequalities are strict. Okay. So this is to avoid pathologies which are never encountered anyway. So, well, you never know. Then, so we want to find a special hyperplane, which we call the optimal separated hyperplane, is the one which stays as far as possible, separate the data, but stays as far as possible from the data points. And so we need to remember what is the distance of a point to the hyperplane, right? So then there is a formula, which is written here, right? So if I have my hyperplane, so I have vector W and a constant B, then a point X has X in the space, and the distance of this point to the hyperplane is given by this formula. So I take the absolute value of my linear function divided by the norm of W. And this can be worked out and is left as an exercise. Okay. Not difficult. So, if you struggle, you can see. I think it's okay. So, so we have this notion of distance of a point to the hyperplane. And now we're going to check the distance of each point of the training set to the hyperplane, and then we'll come up with an optimization problem. We search for the weights W for the vector W and the parameter B, so that this distance is maximized. Okay, such that something is maximized. It's still not very clear. So, distance of a point to the hyperplane. Then the next thing is what we call the margin. And this is a notion which refers to a hyperplane and a full training set. So I have my hyperplane, W and B, and now I define the margin of this hyperplane relative to a training set S or sample is the minimum distance of the points in the training set to the hyperplane. Okay, so it is the smallest. So I have my points, and I take a hyperplane. It doesn't need to, at this stage, doesn't need to separate the data, right? Okay, so it would be just, for example, this one, or this is actually quite stupid one. But so in this case, the closest point is this one, and this is the margin. That's it, right? So what we will search for will be for separating hyperplane, right? So which separate the data and maximize the margin. So that's what we're going. Now this is here to confuse you, but sorry about that. But it's if you read books, they call margin also another quantity, which is less important. Yeah. But so if you read papers and books, for some reason, they also call W transpose X plus B the margin. This is to be positive or negative, so the margin of a point. What I call the margin is the margin of the separating, the separating hyperplane relative to the training data. But if you read papers, they also call margin this quantity. And the classifiers that we build here are called margin classifiers. But not important. Oh, eventually we have a picture. So this is the definition of the optimal separating hyperplane, which is also called linear separating SVM. That's the same. So SVM will work in kernels, may not separate exactly the data, but in the special case, if you separate the data with a line, it's what here I call optimal separating hyperplane. It's a special case of an SVM. So here we look for, so not what is written here, so I first say words and then we go through the equations, to the details. So here we look for a separated hyperplane which maximizes the margin for the data. Actually, that's quite short phrase. So what does it mean? It means that we will try to maximize over W and B. These are the parameters of this line, which also gives my classifier. And then I will maximize the minimum over I. I runs over the index of the data from 1 to n, right? And what I will minimize is the distance of the point xi to the hyperplane. And now notice here that instead of putting the absolute value of the numerator, I put yi times the linear function, right? Okay. And then I have this constraint, which are the separability constraints. So the interpretation of this complicated problem, now we will simplify it in the next slides, is that we can solve this optimization problem. We find, at this stage it's not clear that it will be a unique solution, but if you look at the picture, it should be kind of, the picture should suggest that the solution will be unique, or we'll see it later. So if we can solve this problem, we will find, and our assumption that the data is separable is correct, so data are separable. Data points are separable. As to solve this problem, we'll find the line to separate the data with the largest possible margin. So,
one question.
Yes.
Why is it in this case y times wxi instead of the absolute value as in the previous equation?
There's a question in the previous slide.
Yeah.
What do we have there?
We had the absolute value.
Yes, yes. The reason is that since you have this constraint, yeah, I could have actually written the absolute value. Correct. So what is important is that I have this constraint. And since I have this constraint here to align the part that's the same sign, I could have put the absolute value. Yeah, that's a good point. Yeah. So, yeah. Other questions? So it's okay. Please ask. So now we want to understand a bit more how can we solve this problem, and so like we did last week in the case of ridge regression, what are the properties of the solution, and then how do we extend the linear functions. So this is pretty much the plan of the lecture, the remaining part of the lecture. Yeah. So, the first thing is we need to understand a little bit. This is kind of more of a detail, but it deserves some parentheses. That the separating hyperplane, so as we said, it's parameterized by W and B, right? So the weight vector and the threshold B. But so this choice is not unique, right? Because if you scale these two pair, this pair by constant, you have the same separating hyperplane. So basically, this notion of separating hyperplane is invariably scaling by constant parameter. So somehow we want to resolve this issue because we'll solve an optimization problem, and then we would like to ensure that there is not this redundancy of parameterization. So there is this mathematical issue. So one way to go around this is to is either to work with what is called a normalized hyperplane or canonical hyperplane. These are more mathematically, as I said, less important than what I said before. But let me describe it. So one way to kind of fix the representation is to use the convention that the norm of the weight vector is equal to 1. You can always do that, because as I said, you can fix this. So this is a way to fix this scalar. It's equal to 1. So what is the consequence of this is that the distance of a point to the hyperplane is just the absolute value of W transpose X plus 1. So simple form. Okay? And so in this case, and the margin then would be the minimum of that thing, the margin of separation. So the equation is simple. And this is, yes, this is one way. The other way, which is the way that we will use in analyzing and working out the optimization problem further, working out the previous optimization problem, is to use this canonical representation, which is a data-dependent representation. Right? So the previous one does not depend really on the data, it depends on the W is equal to 1. The second one chooses the norm of W so that the margin of the separating hyperplane is 1 over W. It was 1 over the norm of W. So in other words, we require that this the minimum of this quantity, right? So which is the product between the label and the value of the linear function of the data is equal to 1. Sorry. Yeah, it's equal to 1. Let's yeah. So these two representations allows us to further massage the optimization problem, right, which is one. Okay. So now we're going to analyze this problem in two cases, and we will simplify it. And then we will understand the problem. So there is some algebra and some geometry. So, yes. So if we work with the first normalization, so we have to solve this problem, and that's it. No more to say. Not very nice because it's a difficult constraint, so we will put this aside. If we work with the second representation, so the canonical representation, so we work with the canonical hyperplane, as I said, and let's go here. So this will be equal to 1, right? Because I've chosen the. So here I put 1 over the normal value. So I replace all this stuff by 1. Right? So I need to maximize, right? And this minimum here is not there anymore because the minimum will be 1 over the normal value. So I I remove the minimum. And here I have 1 over W. But then in the constraint, I need to put the choice of my parameterization as a constraint. So, right? So I write this. I write that. This is the choice of this canonical representation. And then I have the scalability constraint. But if I combine these two constraints, as you see, I find this constraint. So this constraint and this constraint together, they can just be written as a constraint that a function times quite I is more or equal than 1. So I have a little gap. So it's not more or equal than 0, it's more or equal than 1. And so this one here is the same one here. So that's it. So the problem is equivalent to maximizing over the parameters 1 over W sums to this constraint, and this is the same as this quantity is equal to 1 over the minimum of the norm of W summed to the constraint. So in summary, the problem that I have to solve is this one. If I solve this problem, and here I've written it more in this form, so I have squared the norm, so I have W transpose W, quadratic function. To maximize that, substitute this linear constraint. So I have a quadratic programming problem. This is called a quadratic programming problem. And it's a problem with minimizing a quadratic function subject to some linear constraint. It's called quadratic programming problem. And it is an easy problem, or principle, is a convex optimization problem because the objective function is convex. So W transpose W is a convex function. So not only is it quadratic, but it's convex. So the Hessian is positive, symmetric, definite in this case. So it's strictly convex. So there's some theory which says that if you minimize a strictly convex function, right, which grows as infinity, so as W becomes larger, the function becomes larger and larger. So the minimum will not be down there, but it will be somehow here. So if the function is convex, grows at infinity, then there is a minimum, and if it is strictly, so the Hessian is positive definite, the minimum is unique. So there is a unique solution to this problem, which is our optimal separated hyperplane in the canonical representation. So the margin is 1 over the number. So this is a bit dense to all this stuff. So, yeah, that's it. That's the. So we arrived to one first conclusion. So we have, if we want to do this linear SVM with separable data, we need to solve this problem. Now, after the break, we will try to understand. We will try to, how do you say, to understand the property of this. So we stop for 10 minutes, don't wait.